Okay, so picking up with where we got cut off before, if you move over to page 2, and I'd kind of already started talking about some of the information that was on page 2. So we were looking at atomic structure. If you roll over to page 2, the design of an atom, I was kind of already covering that as well. So understanding that you have that central core that gives us off a positive charge, depending on how many positives you have in that nucleus, will ultimately determine how many negative charges are then drawn towards that particular atom. Now, I indicated that that first layer around the atom would hold a maximum of 2 electrons. The second layer would hold a maximum of 8. Now, the reason that that is important is because if you look at the second slide on page 2, it talks about the goal of atoms. And in the world of chemistry, you guys have all seen situations where you mix two things together and nothing happens. And you take two different things and you mix them together, and now you've got bubbles and gas and all sorts of things happening. So, what's the explanation behind that? Why can you put two things together and nothing happens, and you put two other things together and now you've got all this um, explosiveness that's taking place? Well, the reason is explained in that second slide. The goal of all atoms is to make sure that their outermost shell is completely full. And I keep mentioning in a perfect world, the number of protons would equal the number of neutrons would equal the number of electrons. And in a perfect world, yes, it would. But we don't live in a perfect world. And so these atoms are working very, very hard to make themselves happy. And how do they accomplish that? They make sure that their outermost shell is completely full of electrons. That is their whole purpose in life. And so if they're working to get that outer shell completely full of electrons, that would explain why sometimes you put things in the vicinity of each other and those electrons are moving back and forth between those elements and you get reactions to happen. In another case, you might have two things that are already full, and so they don't need to have that interaction, and so you're not going to see any of that explosiveness take place. So if we look at hydrogen, hydrogen is number 1 on the periodic table. Perfect world says we know its atomic number is 1. That tells us definitely how many protons it has. We will assume it has 1 neutron and 1 electron as well. So if you go back to what I was saying a few minutes ago about the electrons, that first layer or area around the nucleus is going to hold a max of 2 electrons. So in order for hydrogen to be happy, there has to be 2 electrons there. But being number 1 on the periodic table, it naturally only has 1 by itself. So hydrogen is going to work to go out and find somewhere where it can pick up another electron. So if it finds another electron, it'll have its 1 proton in the nucleus, its 1 neutron in the nucleus, and now it's going to have the 1 electron it had on its own and the 1 that it picked up from somewhere else. Now it's got 2 electrons, that outer shell is full, and hydrogen is happy. So in the arrangement of slides that you guys have, if you look at the very last one, it talks about the types of bonds, and that does an explanation for exactly how different elements can accomplish getting their outer shell full. And there are other ways beyond these two, but really for our purposes, we just need to know these two. So bonds allow for atoms to interact with each other in a way that they can either share their electrons and complete their outer shells, or they can give and take electrons between different atoms to get their outer shells completely full. So in the case of a covalent bond, what happens is you have two elements or two atoms that are going to share and work together to fill their outermost shell. So just a second ago, I was using the example of hydrogen. Hydrogen is number 1 on the periodic table, has its 1 proton, 1 neutron, and then that 1 lonely electron hanging out. It's looking for 1 more electron to get that shell to 2 electrons, be full, and be happy. So a lot of times hydrogen will just bond with another hydrogen because the other hydrogen also has 1. If they come together and share 1 electron from this atom, 1 electron from this atom, and they come together, now they're sharing, they have 2 electrons, and both of them are full, both of them are happy. So that would be an example of a covalent bond because those atoms are working together. They are using their electrons to get their outer shells full. In the case of an ionic bond, we have to look at the root word of ion when we talk about ionic bonds to really understand what that means. So ion means that an element carries a charge, and ion doesn't really identify. It could be a positive charge, it could be a negative charge. But if the element has any charge to it whatsoever, we call it an ion. So how would this be accomplished? If you have a situation where you have two atoms and neither one of their shells are completely full, one atom can kick out some of its electrons and get rid of them. And by doing that, it will get its outermost ring completely full, because you don't have to necessarily gain electrons. You can give up some of your electrons and get to a shell that is completely full. And we'll talk about that a little bit more. So in the case of, let's say we're on the periodic table and element number 3, 3 protons, 3 neutrons, 3 electrons. Well, if you start placing that, you have your 3 electrons. So 2 of those electrons would go in the first shell or the first orbital. That extra one now has to be placed in that next layer because there's not enough room for it to fit in that first layer. Only 2 can fit there. So the first to go in the first layer, we've now got this third electron hanging out all by itself in that second layer. And here's the problem. When you look at that second layer, it can hold a max of 8. So now this element has to decide what is going to be the easier route to take here. Is it going to be easier to go out and find 7 more electrons to fill my outer shell and get it bumped up to 8? Or is it going to be easier to kick out that 1 electron, give it up? Now that second ring is no longer needed because that electron is gone. We drop down to just having that first one again. That already has its 2 electrons. It's full. It's good to go. Well, obviously, path of least resistance is not going to be to gain 7. It's going to be to kick out 1. Now, what happens then is, if you think about this, it's 3 on the periodic table. It means that it has 3 protons, 3 positive charges. It also used to have 3 electrons, 3 negative charges, but we kicked out one of those. You can see I'm painting today. You kicked out one of those electrons. So now we have 3 positive charges. We have 2 negative charges. And now the charges are not going to balance. We have 1 more positive than we have negative. So now this atom is going to have a +1 positive charge. That's an ion. On the other side of things, you have that 1 electron that is floating around. And let's say that it found a hydrogen and that hydrogen picked it up. Well, a hydrogen all by itself, if it picked up that 1 electron, okay, go back to periodic table, it had 1 proton, 1 neutron, it had its own electron, but now it just picked up that electron that was floating around on its own. So our 1 proton hanging out in the nucleus, now we have 2 negative charges. Because we have more negative charges than we do positives, now that hydrogen is going to carry a negative charge to it. That would also be an ion. So when you use the term ion, it doesn't matter if it's a positive charge or if it's a negative charge, but if it goes either way, positive or negative, we just use that term ion. So when we talk about ionic bonds, the reason that that term is used is because in the shifting of those electrons, the give and take, one atom is going to pick up some extra electrons to fill its shell. And by picking up those extra negative charges, it's going to take on a negative charge to the entire atom. That's an ion. The other atom that gave up its negative charges, okay, kicked them out, got rid of them, now it has fewer negative charges than positives. And so that atom is going to give off a positive charge. That is also an ion. So we use the term ionic bond to indicate that because those electrons are shifting back and forth, the charges on the elements is not going to be neutral anymore. They're either going to become positive or negative, and we need to refer to them as an ion. If you flip over to page 3 talks about water. And why would we spend time talking about water? Water doesn't seem very exciting. Water is actually a very amazing element in the world of chemistry because of the things that it can do, and we really don't give it enough credit. And the reason for that, I think a lot of times is because it's so much in our daily lives. We drink it, we bathe in it, we swim in it. We don't think twice about it. It's just neutral in our minds. It's a very tame thing. And so, why would we really care how water behaves? And the reason for that is because water actually behaves very differently than most of the things that we see in chemistry. And usually, when you start getting into things that bond together, so if you look at the chemical formula for water, it's H2O. The two behind the letter H tells us we have two hydrogen. We have nothing behind the oxygen, so it's an understood one. So we've got two hydrogens, we've got one oxygen that are coming together to form this water molecule. Now, the thing that's important about it is that in the making of this particular molecule, it doesn't form like most. In the world of chemistry, when you have different elements come together, usually you have your large element, your largest one in the middle, and then all the other ones that are linking to it will be equidistant from each other. They kind of want to stay as far apart from each other as they possibly can. In the case of water, it doesn't do that. You have oxygen, which is the largest molecule. It's 8 on the periodic table. Hydrogens are 1. So if you've only got 1 proton, 1 electron, 1 neutron, and oxygen has 8 of all of those, you can see why oxygen would be bigger. It's got more particles to take care of, to have space for. So you have this larger oxygen molecule, but the two hydrogens don't go on opposing sides. So it's not like the North Pole and the South Pole. Typically, that's how other molecules would attach to that large molecule. But what the hydrogens do is they actually attach to the same side of oxygen. And when you draw it out, it kind of looks like a Mickey head. You have the large round head, and then where the two ears would be, that is essentially what the water molecule looks like. But it's like I said, very different. We typically don't see that arrangement in the world of chemistry, and that allows water to do things that we don't see in other molecules either. And actually, the entire ability to keep life going is very dependent on the properties that water is able to have or possess because of that specific arrangement. So, what happens in the case of water is you have that large oxygen in the middle, and it acts as a bully. So, even though it's a molecule and they're all technically working together as one unit, the oxygen will actually take the electrons from the hydrogens and pull those electrons closer to itself. So now, essentially, oxygen has two extra negative charges. So it gives off a negative charge. It took the negative charges from the hydrogen. And so now the hydrogens really don't have any electrons. They only had one to begin with. Oxygen stole them away. And so now the hydrogens really only have a positive charge. So when you think about that arrangement of the water molecule, the oxygen side of the water molecule is going to act positive, or excuse me, is going to act negatively. And the hydrogen side of the water molecule is going to act positively. Well, what does that sound like in the world of things that you are familiar with and you probably work with or use on a daily basis? It's like a magnet. Magnet has a positive side, it has a negative side. Now, in the world of chemistry, we call these polar molecules, and there are other examples of them, but they're rare. They're not a common thing to have. So anything that has a magnet-like setup where one side of the molecule behaves positively and the other side of the molecule behaves negatively, that's a polar molecule. This allows water to do some things because the hydrogen, being positive, is going to have a very strong pull or draw to a negative. And so water molecules actually have a little bit stronger attachment than your average molecule because of that positive side and that negative side being drawn to each other a little bit more than your average molecule would be. The other thing that this does is some of the things that we see. You guys know that when you have ice, okay, ice is less dense when it's frozen. That's not usually what happens with things. When they become colder, they become more dense, they would sink, and that's not the case. Ice will actually float. You guys know if you put it in a drink, a soda or a cup of water, it's going to float to the top. Why is this important? It's important because of the fact that think about our rivers and our ponds and things like that. If ice went to the bottom and froze from the bottom up, anything that was alive in there is going to be killed. And so our waterways every winter would have nothing left in them as far as life goes. So the fact that the top layer freezes and the underside of our rivers and our ponds and streams and things like that stays liquid allows for those things to go to the depths and stay down there during those winter months and survive. So there's a lot of features of this property of water that is very, very important. If you look at the dissociation of water, the other thing that I think kind of surprises people is when we talk about chemistry, people talk about acids and bases. That's just a easy connection to make. But the basis for where acids and bases actually come from is water. And when you take a water molecule, that H2O, there are certain situations where that water molecule will break apart, and it doesn't break apart evenly. So the hydrogens don't go off on their own and the oxygen doesn't go off on its own. Instead, what happens is the oxygen will stay attached to one of the hydrogens and the other hydrogen goes off on its own. Go back to that arrangement. Oxygen keeps all the electrons. So it carries extra electrons with it. And so even when that oxygen and that hydrogen go off on their own, they have more electrons than they should, so they have a negative charge to them. That hydrogen that gets kicked out and leaves on its own, nobody else with it, has no electrons. It only has its proton. So when it gets kicked out and goes off by itself, it gives off a positive charge. So you have OH negative, so that oxygen and that hydrogen that stay together, one oxygen, one of the hydrogens, they stay together, they're carrying a negative charge. It's OH negative, and we call that a hydroxide ion. The hydrogen that goes off on its own, carrying that positive charge, is called a hydrogen ion. How does that relate to acids and bases? OH negatives, those hydroxide ions, those are what make up a base. Those hydrogen ions that are hanging out by themselves, that is what makes your acids. So you take this very tame substance of water, has a pH level of 7, it's neutral. And when you break it apart into smaller components, one of the hydrogens, one of the oxygens, you get the substance that makes up your base. And when you take that hydrogen by itself, you get the basis for you get your acids. Now, depending on how many of those hydrogen ions you have in a substance will determine how strong your acid is. And the amount of hydroxide ions that you have in a substance will determine how strong the base is. So that takes us to our pH scale. pH scale is a very interesting tool because of how it's set up. Usually you start at 0 when you have a measurement tool and you work your way from there. But when you look at the pH scale runs from 0 to 14. 0 is the lowest number that you can have, 14 is the highest number you can have. But really the baseline is 7, that neutral point that we have. At 7 on the pH scale, you're halfway in the middle. Okay, you're as far away from 0 as you can be, you're far as away from 14 as you can be. So at 7, being neutral, there are no acidic properties, there are no basic properties. As you move from 7 and get closer to 14, there's a little bit of a shift because in all of our acids and bases, you do have some hydrogen ions and you do have some hydroxides. It's just the amount you have of each one that tells you, again, how strong that acid or how strong that base is going to be. So at 7, number of hydrogens and hydroxide ions is the same, so they cancel each other out. 7, neutral point. As we go from 7 and we get closer to 14, okay, the number of hydroxides that we have is going to increase and the number of hydrogen ions in that liquid or that solution is going to decrease. On the flip side of that, if we're at 7 and we start to work towards 0, now the number of hydrogen ions that we have is going to increase and the number of hydroxides in that solution is going to decrease. So please keep in mind that in your acids and your bases, you do have both hydrogen ions and hydroxide ions present. But the amount is going to fluctuate depending on which side of 7 you're going. If you're going closer to 14, the number of hydroxides is increasing. If you are going towards 0, the number of hydrogens is increasing. Now, on the pH scale, I mentioned it goes from 0 to 14. Every time, and that doesn't really seem like a big scale, but we have acids and we have bases also that are very, very strong. They can burn through human tissue very easily. And to have something that can do that much damage, what you have to understand is if we're at 7 on the pH scale and we move down to a 6, even though that's only 1 point in our minds, the strength of the acid going from 7 to 6 is actually going to increase 10 times. So if you go from 7 to 5 on the pH scale, it increased 10 times when you went from 7 to 6. It increased another 10 times when you went from 6 to 5. So now just going from 7 to a 5, the overall strength of that acid increased 100 times because you have 10 times 10. So if you think about starting at 7 and then by the time you get all the way to 0, how much that acid has increased in intensity, it gets pretty high. Likewise, people hear the word base and they think, safe. Every time you have base in games or anything like that, base is always where you want to be. Base is just as intense as an acid is. So again, moving from 7 up to 8 is going to increase the strength of the base 10 times. If we went from 7 to 9, now the strength of our base has increased 100 times because we went 10 times from 7 to 8, another 10 times going from 8 to 9. So even though the scale overall seems very, very small, the intensity and the strength of those acids and those bases does jump up very, very quickly. The last 2 pages that we have talk about organic and inorganic substances. And I'm going to kind of hold off on this for right now. Some of this will pick up in other conversations that we have along the way, especially when we get into the digestion chapter. So for our first lecture, I'm going to stop it right here. Just please make sure that you carry this chemistry packet with you in the future and the next couple of classes, because we do kind of come back to different packets. A lot of the information that we deal with week in and week out is going to build on the previous topics and conversations that we've had. So I always ask you to make sure that you guys have your packets with you so that when those jump up, you have everything that you need with you. All right, so for your assignment this week, you were given some anatomical terms and you had the label sheets. We went through those with the anatomical terms. Please make sure that you spend some time with those and start to commit those to memory. I had indicated the other night that those would pop up at different times. So please make sure that you are becoming familiar with that. The other thing that I would like you to do, and this is going to be specifically for next class, is the directional terms. So you had the anatomical positions. This is different than the anatomical terms. So the anatomical terms deal with the placement and the structure on the body. The anatomical terms are more directional terms. So we had the anterior and the posterior, the dorsal and the ventral. I would like you to make sure that you are very comfortable with those and that you could answer questions without that sheet. So it's not a quiz, but you are going to have an activity. And as I just mentioned, you are not going to be able to use this as a resource. So please make sure that you are spending some time with it and getting to know those terms for what we are going to open up class with the next time that we meet face-to-face. So I will see you guys on the 25th. If you have any questions or need anything prior to that, please send me an email. I will be checking my St. Luke's email on a daily basis. My other email, I check on an hourly basis. So whichever, if you need quick feedback, I would do my school email. If you can wait a little bit before you get a response, you can use that St. Luke's email, whichever one you are comfortable with. Like I said, if you have any questions, just let me know, and I will plan on seeing you on the 25th.